Assalamu alaikum. Hello, everyone. We continue the topic of data understanding and preparation. So last time we stopped here at conversion. Okay. So in fact, I was recording last time. I just moved it to PowerPoint slides in order to explain this visually in a better way. And I thought that I was sharing the whole screen, but it turns out that I was sharing only the browser. So all the explanation I was doing, it wasn't showing in the video, so I had to remove that part and record it again. Okay. Now let's me move to the PowerPoint slides in order to explain these visually. So I'm using some of these plot images or figures in the PowerPoint slides here, but yeah, maybe here is I can at least use the pen or the pointer to explain things in a better way. Okay, so most of the models work with numerical data, so we need to convert categorical attributes to numerical attributes before feeding them to our models, okay? So, and that conversion depends on the type. Is it nominal or ordinal? Okay. And here I'm violating the terminology a little bit. So the terminology we used in this course. So because we say nominal is a numerical representation of a categorical attribute that has no order. I would just say categorical nominal in that sense, in that case, okay? And in fact, it's used, okay? Categorical nominal and categorical ordinal, because according to what we have defined in topic 2, nominal is a numerical representation for where there is no order, just for convenience, okay? But let's say, for simplicity, we don't want to say, okay, we convert from categorical to nominal and then encode it. Let's just do it direct, okay? That will simplify things. So we will say categorical nominal and categorical ordinal, and they are encoded in different ways, okay? But before I explain this, let's assume, for example, let's start with this very simple label encoder, okay? I'm given a number of, like I'm given an attribute that actually can take one of these categories. It's a categorical attribute. It can take, the value can be one of these categories, okay? There are 4 categories here. So if I use label encoder to encode this, there is no order here, okay? There is no order, okay? If I use label encoder to encode this, then they will be encoded this way. So 0 is given to apple, 1 is given to banana. I think the numbers are given based on the alphabetical order here. Apple starts with A, so it's given 0. Banana starts with B, is given 1, and so on. So we have 0, 1, 2, 3 for apple, banana, mango, and orange, okay? So here, there is no order here, but there is order introduced here, okay? So there is order here. Orange has higher value than apple, okay, much higher. And the distance between, for example, apple is 1 step away from banana, but it's 3 steps away from orange. So we are introducing an order. But this is actually, there's no order here. Then we shouldn't introduce an order. If we want to do transformation, then we should look for another. If we don't want to introduce an order, and in fact, we shouldn't introduce an order if we have a nominal attribute, or if we have a categorical attribute where there is no order, then when we transform it to numerical format, we shouldn't introduce an order. Then one way to do that is through one hot encoding, okay? So one hot encoding will encode the data as we can see here, okay? It's actually introducing a number of variables that is equal to the number of different categories here, or choices. So here there are 4 categories. Then we are actually replacing then one categorical attribute with 4 numerical attributes, binary attributes, okay? At most 4, we can actually go with 3, as I will explain later. So at least 3, at most 4, okay? We cannot go below 3, and we cannot go above 4. Let me explain that. So now, what as the name indicates, one hot encoding, so one bit or will be 1, or one variable of this will be 1, and the rest will be 0. For example, for red, the first one is 1, and all of these are zeros. If the value is green in the original one, then the second one will be 1, and every other one will be 0. If the value is blue in the original categorical attribute, then the third one will be 1, and the rest will be zeros, or the remaining ones. Okay, so there is only one bit that is 1, and the other bits are zeros. So now there is no order here, but we are introducing more attributes here. Okay, actually we can exclude the first one. Okay, because of these, if these three are zeros, then we know it's red, so we don't need this one. Okay, so we can encode this a categorical attribute with n categories to using n minus 1 variables or new binary attributes. Okay, now one hot encoding avoids the issue of introducing an order, but it creates another issue, which is it's increasing the number of attributes. And as I said, increasing the number of attributes can complicate the learning process. Okay, as I explained it, like as the number of features increases, the number of samples you need in order to train a model increases exponentially with that. Okay, so if you have very limited number of samples, then with many attributes you are introducing, you may run into the problem of overfitting if you are training a model. And we'll come to that later on and explain it, but at very simple words, overfitting is when you get so much concerned about what your training data is telling you, and you don't generalize very well outside of your training data. I don't want to say more about this for now, but that's one issue we face there. Yeah, but we have to go with one hot encoding to avoid a bigger issue, which is introducing an order that wasn't there to begin with. Okay, now if my categorical attribute has order, okay, for example, low, medium, and high, then we need to maintain that order after the transformation. Okay, and for us to maintain that order, we need to make sure that we map low, for example, to 0, medium to 2, and high to low to 0, medium to 1, and high to 2, or low to 1, medium to 2, and high to 3. So we need to maintain that order. In order to maintain that, we cannot do it with label encoder, because this gives the numbers based on the alphabetical, okay, order of the words. It's not based on the order, okay, that is defined in our categorical attribute. One way to do it is actually, I'm including this snapshot for this code from our lecture. So here we map those different categories to their to numbers, such that the order is maintained. For example, here we have a categorical attribute of title education. So we have primary, secondary, and tertiary. Okay, so we know primary comes first in the the lowest in the order. So secondary is higher, and tertiary is the highest. So then we map primary to 1, secondary to 2, and tertiary to 3. So we are creating a dictionary here. We are mapping these to values such that the order is maintained. Then the new version of the column education is equal to the old version dot map. We call the function map, and we pass this mapping dictionary here. So then we convert the categorical attribute that has values primary, secondary, tertiary to a new attribute that has 1 for primary, 2 for secondary, and 3 for tertiary. So we converted this categorical attribute to a numerical attribute, and we have maintained the order. Okay, now I come to the next step. There was something about feature construction. I will talk about that when we go back to the file, to the Jupyter Notebook file. But let me now talk about normalization, which is a step comes after that. Okay, so normalization. Why do we first do normalization? First of all, what's normalization? So we bring all the features to the same scale. I have a number of features. Every one of them could be from different scale. Okay, we are bringing all of them to the same scale. Why do we do that? Okay, let me explain it here. There are two reasons. Okay, the first reason, let me explain it by example. Assume I have two features. One of them like takes numbers from 1 to 9, for example, 1-digit numbers, and the other one is taking numbers at thousands, so 4-digit numbers. Okay, so this is at thousands, and this is at very 1 to 9. So I don't want the one that is that has high values to dominate because of its high values, okay? So that's why I bring all of them to the same scale. So the one that really, the one that is most correlated or related to the output or the target variable will affect the variable more, not the one that is coming from high values. So that's the first advantage of bringing all of the features to the same scale. Okay. The second feature or the second advantage is about the conversion speed of our algorithm, because most of the time when we are running machine learning algorithm, we are running iterative algorithms due to the large size of the data and maybe the number of features. So we run iterative algorithms, okay? And iterative algorithms can get the speed of those algorithms can get so much affected by these different scales. For example, here I have two features, okay? I assume two features. Here, the feature in the x-axis, and this is the other feature in y-axis. If they are coming from different scales, if the numbers here are low and the numbers here are large, okay? If they are coming from different scales, then to reach, we start, as I said, we start with the initial guess for the optima and we keep moving, okay? So if these features are coming from different scales, then we will see a lot of bouncing, and we need to choose a learning rate to be very low. And we will come to all these details later on. It will become clear there. I'm trying to just at very high level explain it here. So we will take so much time bouncing to reach the optima, the minimizer of our loss function. Okay, the loss function that we are minimizing in order to find our optimal set of model parameters. Okay, so it will take so much time. Versus this is elliptical shape here. This is the contour of the function, by the way. I forget maybe to mention. This is the contour of our loss function. Maybe this should have been my starting point. This is the contour of the loss function, okay? And this is our movements toward the minima. So it will take so much time, and we need to set the step size of moving towards the minima. We need to set it to be very low, okay? So the conversion speed to the optima will be very slow. Here, if we are scaling all of them to the same scale, then the contour of the function will be more of a circle contour. Here, the movement towards the minima is much more smoother, and we can go with larger learning rate. We can make it smaller as we approach the minima, but we can start with large one, and we will move faster and much smoother towards the minima, so we can converge much faster. Okay. Now, I talked about the normalization and the advantages that normalization brings. Now, how do we do normalization? There are different schemes, okay? There is min-max normalization, there is z-score normalization, and there is just simple scaling. Scaling, you mean, for example, you divide by the max. When you divide by the max, you bring every feature to be between 0 and 1, okay? In fact, you are going to bring every feature to be between -1 and 1. Okay, if there are negative values. Okay. Now let's come to min-max. Min-max actually what it does, it brings each feature to be to start exactly at 0 and ends exactly at 1. Okay, so all of the features will start from the same point and end at the same point. The starting and the ending, 0 and 1. So how that's achieved? By taking subtracting the min and divide by max and min. So if x is the min, then min minus min is equal to 0. So the minimum point will be at 0. If x is the max, then max minus min over max minus min, that's equal to 1. So the last point will be at 1. So every feature will start at 0 and ends at 1. Okay. This is very sensitive to outliers. So if we don't remove outliers still can have effect on min-max, because assume, for example, there's one outlier that is very high and the rest of the points are very close to the minima. Then even after normalization, you will see like many points very close to 0, and there is 1 point at 1. Okay, so it's still, in that sense, it brings the advantage. It brings all the features to exactly same scale. They all start at 0, ends at 1, but it's sensitive to outliers. Z-score is less sensitive to outliers because it doesn't really bring exactly everyone to the same starting and ending. It's less sensitive to outliers. So if you are not removing your outliers for your problem, maybe it's better you consider Z-score normalization, or we also call it standardization. Okay, what it does, it brings all the points to be centered around 0, okay, with standard deviation equal to 1. So it subtracts the mean. So the mean after the normalization will be 0, and it divides by sigma, the standard deviation. So the standard deviation after the transformation will be 1. So the variance will also be 1. Okay, so every point you take it, you subtract the mean and divide by the standard deviation. So this is the data before the normalization. This was the mean, and this was the standard deviation. After the transformation, the mean became 0 and the standard deviation became 1. Okay, so with that, let me go back to the here. As I said, so this doesn't really bring them to start and end at the same point, but it's less sensitive to outliers. Okay, if you remove outliers before this step, okay, then you may go with min-max. If you don't remove the outliers, maybe it's better to go with Z-score. And you always can try these two and see which one is doing better for your use case or application. So the last thing here to mention is feature construction. In some cases, you may need to actually add more features that can serve your purpose. For example, I will give one example. Assume like you are trying to predict Y with an input feature X, where Y is not linearly related to X, okay, but you have only X. Then actually, if you build a linear model, okay, then the line may not be the best representative of that relation. Then you may consider adding, creating another feature that can be X square or log X, depends on what's the kind of the relation, okay? So you are creating another feature from already existing feature. You have X, then you are creating another feature that is X square or log X or square root of X, depends on what you think the relation is more of, okay? Then you're adding that feature, then you're moving beyond just linear line. Then you can come up with a curve that may represent the relationship in a better way. And we will come to this, like we'll talk about this more when we come to regression problem later on, inshallah. Okay, so with that, we come to the first case study here. So let's look at this case study. Here we are loading this data. Let's look at this data. Okay, as you can see here, so we have a number of features: the country, the population, overall life, male life, female life, continent, and sub-region. Okay, and here are the statistics. Okay, let's work with this data and fix any issues we have there. Okay, so here are the types. They're supposed to be this. For example, population should be numeric, but here there will be inconsistency issue. So we will have here, they will be, these are read as strings, okay? So population is loaded as a categorical column, as we will see later. We need to fix that issue. Okay, what are other issues we have? We should run info to see if there are missing value. Here, let's run this. Okay, so here, in total, there are 25 entries, but for some of the columns or attributes, there is less than 25 non-null elements. That means there is missing data. So there is missing data, and there is one inconsistency issue here. We need to fix those. Okay, let's also see if there are other problems. Okay, here, this is the first one we fix here. As you can see, according to here, to the outcome of info, population is the data type here is object, but actually here the number should be the data type should be integer because these are numbers. Okay, so we need to fix that issue. So now it's loaded as object. We need to fix that issue. Simply the new version of the column is equal to the old version. Apply this function. This function removes the comma, replaces comma with nothing, removes the comma. Removing the comma itself is not enough. It will not convert it to integer. It will just remove the comma. Then we need to pass it to the integer method. So we cast it as an integer. Now we remove the comma and we convert it to integer, okay? So if we print out info after that, you see it's integer here. Population became integer, okay? We fixed the first issue. Now, another thing here, these three columns here, okay? These columns here, overall life, male life, female life, all of them are percentages. So we know they should be always positive. So to avoid a scenario like, for example, someone maybe by mistake entered a negative sign, okay? So to make sure that they are all positive, we can actually call this code here. We extract here the numerical columns, and then we go over those columns, okay, over each element of these columns, because we're calling apply map. By now we are familiar with this syntax. I don't need to spend time explaining like what the syntax of the function. Simply here we are extracting those numerical columns, and then we are going over every element and we're taking the absolute value of that, just to make sure that we don't have that scenario where a number like one of them is entered as a negative number, okay? So just take the absolute value of that. We are sure now they are all positive numbers, okay? Yeah, and another issue we are fixing here, okay, these are meant to be percentages, but you know, people sometimes like percentage, for example, 70%, someone could enter it 70, some other one could, another person could enter it as, let me display the whole here, okay? So 70%, you may enter it as 70, you may enter it as 0.7, right? For example, here, this one, okay? This one, now we are entering percentage here, okay, out of 100, okay? But this entry was entered, the percentage was entered out of 1, okay? 0.845, this, okay. So we either convert this by multiply it by 100, or we divide this by 100. So we have to bring them all to the same scale. They all need to be out of 100. As I said here, you see the data here, there are some negative values here. Okay, that's why calling that function of absolute, we avoid this scenario. And multiplying by 100 the numbers that are less than 1, we also avoid the problem of having different representations of the percentage. So this is what we do here. Did I run this here? Okay, I should have run this to get rid of the negative values. Now we have no negative values anymore. And then for this one, we go over each one of them. And if x is less than 1, then we multiply x by 100. So we are sure now all of them are in the same scale, no negative numbers, everything is okay. Oh, I didn't run this for the code of for the population. Okay, I run it, right? Okay, then population here is a number. Okay, then why it's not changing here? Okay, let me just run again. I don't know what happened. Okay, yeah, because I rerun that cell after I run that. Yeah, I remember now. Okay, I went up and rerun the first cell. Okay, now things are okay. Okay, so now here, what we are going to do is to, because we have missing values, so we can do imputation or we can drop them, okay? So let's look how do we do imputation and how do we drop, okay? Simply here, we are going over all the columns and we are extracting the columns that has at least one missing value. Okay, let me explain this function here because it's new for us now. Let's first call this df.isNA. Okay, as you can see, first of all, the type here is Boolean. It's a data frame, and the data type for each element is Boolean. It's false. It takes value false if the value is not missing, and true if the value is missing. That's the return of this function, is NA. Okay, it replaces every element with false or true. False if the value is not missing, true if it's missing. Then if we add this here, then it will return a data series, okay, where the labels are the columns, and for every column it's false if that column has no missing value. has no missing values. If the column has at least one missing value, then the return will be true. So for this one, it's true. For this one, is true. Okay. Okay. So we have these two these two attributes have missing values. Okay. So we are extracting these. These are the null columns. Okay. The columns that have nulls, the columns that have missing values. So we extracted these columns. Okay. Then we're going to iterate over these columns. Okay, and iterate. We're going over every column in these columns. If the column type is a numeric, if it's not object, okay, if it's numeric, then this is a temporary variable. If the column is numeric, then the value of that temporary variable is equal to the mean. Else, if it's not numeric, if it's categorical, then it's equal to the mode. And you remember the function mode returns two values. The value of the returns two elements, the value of the mode and the number of occurrences. So we need to access the first one, which is the value. So now the value, if the column is categorical, then value will take the value of the mode. Okay, and then we call the function fill in A, which is going to fill every missing value in that column with the value. Okay, if the column is numeric, then it will fill it with the mean. If it's categorical, it will fill it with the mode. Okay, we can also do median imputation here. Okay, and we are filling in place. So in place is equal to true. So we are performing permanent change. We are changing the same data frame. Okay, that is one way to do it. This is more, okay, there are many commented things here. I'm not going to go over everything. So, but you are responsible to go over everything here for the exam. But I can very quickly talk about some of the commented things here. For example, here, this is just a more concise way to do it. Go over every column, see in columns, and then value is equal to the df.mean if the data type is numeric, and otherwise it's df.mode, and then we call fill in A with the value here. Okay, if we want to drop, there's a code here about dropping. So if, for example, here, if I want to drop all columns containing 20 or more missing values, then the remaining values are what? The shape, the shape 0, the number of records minus 19, right? If you want to drop 20 or more, then we are keeping this, right? So then we can say drop in A, okay, drop all missing values in axis 1 for the columns attributes. How? Any such that the threshold is any less than this threshold. This is the number of non-null. This is the remaining ones because we want to drop 20 or more. Okay, if we want to drop more than 20, this would have been minus 20 here, not minus 19. Okay, so but even like at 20, so 20 or more. So if there are 20, we will drop. Then the remaining ones is the total number minus 19. So then this is the threshold. If the number of non-null less than or equal to this, then drop this column. Okay, and place true equal to true. So we're doing permanent change. We're dropping this column. Okay, we can also drop records. Okay, for example, here we're dropping an axis 0. That's a record. How? All. So what do we mean by that? If a record doesn't have value for every attribute, it's missing the value for all of the attributes, then drop that record. Okay, so yeah, you can play with these, okay, to understand them more. So there, as I said, there's many things here, but I think I explained all of them are the most important parts. Okay, so yeah, maybe let's stop here for today. Next time we go over the second use case for this chapter and or topic, and hopefully next time we finish it, inshallah. Thank you, and see you next time, inshallah. Assalamu alaikum.